Very good morning to all of you. So in the previous lecture, during the previous lecture, what we have covered? We have covered Gauss elimination method. Gauss elimination method, a basic one. Okay, and then we have seen why we have also seen the answer why this basic Gauss elimination method, okay, basic Gauss elimination method fails. Okay, and then we have looked at what are available pivoting strategies. Okay, and then we have seen we can actually handle those cases nicely. Okay, now we are going to look the answer for what will be computational cost. Okay, what will be computational cost for a basic Gauss elimination process? Means we are going to count the number of operations required roughly. Okay, minimum. Okay, so what we have seen, the basic Gauss elimination process actually transform an original system into a new system where the coefficient matrix A is transformed into an upper triangular matrix, and parallelly the constant vector also perturbed with b tilde. Okay, now we have also mentioned there that if you apply the linear algebra calculus, and where we have studied that the elementary row transformations, if you use those transformation, that will not you will not lose the solution. So the obtained system and the original system will be have the same solution, will share the same solution. Okay, so here in this we have applied the row transformation to transform the original system into upper triangular case. Okay, right. Right. So in order to count the number of operations, we have defined the following: one flop is equals to one addition or subtraction plus one multiplication or division. So if either addition happening or subtraction happening, we are going to have 1 plus 1 multiplication or division. So two operations together we will call it one flop. Okay, so with this keep in mind, so let's have here first step is following. So first step is means you are creating zeros below a11. Okay, your aim is to create zeros below a11. So and this is your pivot element. Okay, and this is your pivot row. So by using the first row, you are going to create zeros for zeros instead of a21 to an1, and parallelly these entries are also updated. Okay, these entries are also updated by operations. So here zeros are created, right? Not computed, and other entries are. So how you are creating is you are, so if you wish to create 0 instead of a to 1, so what you are doing is you are multiplying here the row by a to 1 by a11, and then you are subtracting, multiplying, and then you subtract. Okay, So if I collect here, so if I call this, so this is true for this for creating 0 for the second row. In the for second row, first leading element, right? For the third row, you have A31 by A11 and so on. So what are the multiplier for the first step is mi1 is equals to ai1 divided by a11. So 2 less than equals to I less than equals to n. Okay, so these are the multipliers which are used. Okay, so that's first step. How many number of divisions here? N minus 1 number of divisions. If you look at these are number of divisions are n minus 1. Okay, and what are the number of operations? So you are going to updated entries. What will be the updated entry is, so if let's go next slide here. So zeros are created, so for each row we have the multipliers. Okay, these are numbers, how many number them? N minus 1. Okay, we are talking about in the first step. Okay, so therefore n minus 1 division. Okay, so updated entry requires n into n minus 1 flops, which can be understood by the following relation. So what are the updated entries here? Okay, so what are the updated entries? Aij1 is equals to the 4, right? Multiply the corresponding entry and then subtract by the Aij. So you have, if you look it back and see here, so how will you obtain a ith row, a jth column element? So here is this, let's say this is ith row, jth element. So aij1 is updated by, so this aij minus the here ith row, jth column. So right, so here, so it's a first row. So you have a1j time mi1, right? So for this corresponding the for the aij. Similarly for b. Okay, similarly for this is ith row, so bi is going to be updated by, so if you look at here, so what is this is equals to bi minus mi1 time b1. Okay, so you can just make an example and just see the relations. Okay, right. Right, so this is what your first step. So how many so how you are calculating the number of flops? So here you can see here the one subtraction and one multiplication, so one flop, right? So there are how many? This is how many? This n minus 1 cross n minus 1, right? This aij1, this aij is, or this block is of length. So how many number of entries are there? So each entries are updated, so each entry requires a one flop. Okay, so total is so according this block, what will be here, if you see, this is n into n minus 1 block, right? This is no n minus 1 rows. Okay, so this, if I talk about this block is of order n minus 1 into n. So number of columns are n and number of rows are n minus 1. So means total number of entries are n minus 1 into n, and each entry require one flop to update, right? So how many number of flops? So the updated entry requires n into n minus 1 flops. That is can be understood by the following relation, right? So first step requires what? So if you go for see, first step requires n into n minus 1 flop. plus n minus 1 divisions, and so on. So you have to repeat the similar process for the second step, right? Means you are going to reduce n by n minus 1. So first step will have n into n minus 1 flop, okay, flop plus n minus 1 division. If I denote capital D for division and F for flop, for the second step you have n minus 1 into n minus 2 reduced by 1, F flop plus n minus 2 division, right, and so on. So if you make it more clear here, what is here is, okay, so if I wish to write in more way, okay, so you have, so first step you are having n into n minus 1 flop plus n minus 1 division, so that is equals to n square minus n flops plus n minus 1 division. That's the first flop, okay, for that's the first step, okay. For the second step you have the first step. For the second step is a previous n by n minus 1, so n minus 1 square minus n minus 1 flop plus n minus 2 division. Similarly, for third step, you reduce one by more 1, n minus 2 square minus n minus 2 flop plus n minus 3 division, and so on. So what you will have here is 1 square minus 1 flop plus 2 or means last here is 0 division here, okay, right. So you can see n equals to 3, right, will give you this, okay. So this is the last step, you have 0 division, right, okay. Okay, so what if you collect the total number of steps here? So you can see the see here the pattern. Okay, so you have pattern is you have if you total number of flops is n square plus n minus 1 square plus and so on plus 1 square, right, minus n plus n minus 1 plus n minus 2 plus and so on plus 1. This is not total number of flops. So you are having total number of flops, okay, right. Okay, and this is total number of flops plus, now division is n minus 1 plus n minus 2 plus n minus 3 plus and so on plus 1. So sum of n minus 1 natural numbers and division. So you can perform the sum for them. So summation n square, you know, okay, summation n square is, you know, if you apply this summation n square formula, that is n into n plus 1 into 2n plus 1 by 6, and some, you know, sum of n natural number is n into n minus 1 by 2, okay. So if you use them, okay, so what will be the total number of count is, so you will have, so you have, this is here is summation of n square, okay, this is here that a summation of n in that n minus 1 natural numbers, and that is n into n minus 1 by 2 divisions if you to go for it, okay. So if you open up, this is what is, this is, if you see, this is of n cube by 3, right, is of order. Highest power is n cube, 2 by 6 is 1 by 3. Okay, so this is how the number of operation for Gauss elimination will be of big of n cube by 3. Okay, and you apply, so again, if you so for the final step, what is there is apply back substitution method to solve the system at the end, and so it further requires how many flops, and divisions are n number of divisions that you can also count. That's very easy to, okay, back substitution. Okay, so if you go for back substitution, and you have each step require one division, so n number of divisions will be there. That's very clear. And what about the flops? Okay, because you have, if you go back and check this, xi is equals to 1 by AI in the updated one, AII time BI, and these are updated one, okay, which okay, so BI minus summation AIJ XJ, where J is from, okay, J is from I plus 1 to n. Here I are going for back substitution, right? J is equals to I plus 1 to n. You are going to use them from the previous. So one is one division here, one division is there, and one subtraction is there. So here is one division, so that is already count, that is n number of divisions. These are n number of divisions, and here you have a. So this first step have one flop, second step have two flops, and so on, and as a last step will have n minus 1 flop. So total number of flop is summation of n natural number, okay, with last entry is n minus 1. So you have this n minus 1 by 2 flops. Okay, okay, so if you collect both the information, so total system, so total process or finding the solution, what it will have, the entire Gauss elimination method will need the big of n cube by 3 number of operations, right? Okay, so this is how this is the cost of the computation, cost of this Gauss elimination method is big of n cube by 3, right? Okay, so last also we have mentioned somewhere that during the Gauss elimination process, if basic Gauss elimination method is not failing, okay, it does not fail, then you can actually have LU-Factorization from there straightforward. How? So during the Gauss elimination process, you have transformed the AX equals to B to UX equals to B tilde. So during that, what you have observed, what you have obtained, I have specifically mentioned, okay, during that process, that multipliers, pivot, multipliers, right? That's more important. Basic Gauss elimination, we are using the multipliers, right? So if you arrange that the multipliers in a nice way, okay, then you can actually find the L into U part. Okay, so what is there? So if we rearrange the multipliers in an unit lower triangular matrix, means diagonal entries are fixed by, so you have diagonal entries are fixed by 1, and if we rearrange the multipliers in an unit lower triangular matrix by setting Lij is equals to Mij for I not equals to j. So for the first step you have used this m, so Lij is equals to Mij for I not equals to j. Then it is easy to see that A is equals to Lu. So U is as it is, what you have obtained in the final Gauss elimination process. And what we have here is, for the first step, you have the multipliers M, this is M to 1, Okay, M21, M31, M41, and so on, Mn1. So for the first step, okay, right here M22 is 1, so M32, M33, and so on, M3n, okay, and so on. Okay, so if you in the first step multipliers, so first step multipliers means you are using this is what we have called is a I 1 divided by A11, right? Okay, AI, so that is this is what MI1. Okay, AI1 by A11, so M1, so you have this is M11 is 1, M21 is A21 by A11, M31 is A31 by A11, and so on. Okay, so this will give you, so 2 less than equals to I less than equals to n for the first step. So if you make them in the put them in this lower triangular matrix in for by setting Lij is equals to Mij, so L21 is M21, L31 is M31, and so on. Okay, so for the second step you are going to put them in the second column. For the third step you are going to put them in the third column below the principal diagonal. Okay, and then you will obtain the corresponding lower triangular part. Okay, so if you recall that example, so we have seen this example, okay, and we have found the upper triangular part is here, and if you notice these are the multiplier for the first step, 2, 1 by 2 and minus 1. Okay, for the next step we have the multipliers 3 and minus half. For third step you have this multiplier. So if you erase all of them, okay, then you can this is your L part, this is your U. So by using Gauss elimination you are actually finding Dirichlet's decomposition here. So directly, if basic Gauss elimination method will not fail. Okay, so you are actually finding Dirichlet's decomposition by this setting directly. Okay, right. So you can refer that lecture, okay, that previous lecture where we have discussed the multipliers, okay, and then just match with it. Okay, right. Okay, so the another special system is a tri-diagonal system. That's again a special case of Gauss elimination process. Okay, so what we say, the definition is a square matrix A is said to be tri-diagonal if you have zeros for all pairs that satisfied I minus j is greater than 1, or you can say greater than equals to 2. Okay, so means you have main diagonal, so you have main diagonal, so above one more diagonal is there and below one more diagonal, so and other than entries are zeros. Okay, so this such type of system is called tri-diagonal system, and you don't require much number of operations to make it, to transform it into an upper triangular case. Okay, so that you can check. So I just wish to here, so here is, so you have the above entries are here zeros and the below entries are zeros. Okay, so this is here is it's happening. So now you have to create this zeros, a1, here is a2, and so on till this, and then use back substitution method to obtain the solution of the system. Okay, so create the zeros will lead you only one step, so you have to see the multipliers. Okay, so for making zeros what you have to do is, so you have to multiply it by, so if I recall, you have to multiply by a1 by d1. Okay, for creating zero here. Okay, and then so d2 is updated by d2 minus A1 by D1 times C1. Okay, so parallelly on this side also this entry is updated. Okay, similarly for this A2. Okay, so you are going to write. Okay, so you require only one step for that. For now, after updating this is 0 here, so then you are going to use this row. Only single step is required. For say second one is also single step and so on, and then it will create the zeros for the below diagonal, below main diagonal you can say. Okay, and then it will be easy to apply the backward substitution method. So what are the operations? It roughly can okay, so here if I see, so you have D2 is or you can say DI's are updated by DI minus, okay, DI minus a I minus 1 divided by DI minus 1 time Ci minus 1 if you take it carefully. Similarly, BI's are also updated, that BI minus AI minus 1 by DI minus 1 time BI minus 1. Okay, so this is up, these are updated entries. So each step, so for first step is I, okay, and then I equals to 2, for second step I equals to 3, for third step I equals to 4, and so on. Okay, right, and you can solve the triangle system. Okay, so that I can left as an exercise for you. Okay, if you will not be able to follow, so we will discuss in that in a solving session, doubt sessions. Okay, right. So next we are going to learn a very important concept which is very much required to look the error analysis, okay, during the entire process of iterative methods, okay, for solving the system Ax equals to b. Okay, so like we have seen some of the type of condition numbers in during solving the non-linear equations f of x equals to 0. So similarly, we are also going to obtain a condition number for the matrix part. So there we have used the magnitude, right, modulus function. If you recall, okay, if you recall the conditional number, that is x time f dash of x by f of x with magnitude. Okay, so magnitude, so modulus, so positive sign. So for the single variable case it's fine, but for the more than one variable, you need to define some of the way approach to identify the relative error or absolute errors. Okay, so for them we are going to assign norms. So that norms definition you must have learned during your linear algebra course. Okay, so let V be a vector space. So when we will call a set is a vector space if it is associated with two operations. Okay, so you say V is associated with two operations plus and with some means this is dot. So there are two operations. So one is called, this plus is called vector addition, and this dot is called scalar multiplication. So over a field, so you require a field F, so which or a field F, so which is either in our case real or complex. Okay, so if the vector space, we say that V is a vector space if it is closed with respect to addition and scalar multiplication, and it satisfies some of the additional properties, okay, that commutative law, associative law, okay, with respect to addition, okay, and left distributive law, right distributive law, and so on. So you revise your concept for your vectors. So when you will say is a set is a vector space, okay, so revise, okay, revise that v, when you will say a v is a vector space, okay. So we say that a norm is a function. So a norm is a function always defined from a vector space to a set of all non-negative real numbers. Is a function that copies the following properties. So if you take a non-zero vector, the norm is remain greater than 0, okay, right. Non-negativity, you can this is called non-negativity. So means this also tells you, norm of x equals to 0 if and only if x equal to 0. If it's x is a 0 vector, then only norm x is 0, or norm x is 0, then x must be 0, okay. Now second property is mod norm of lambda x. So lambda is real number, okay. So in later case you can have lambda could be a complex number as well, okay. But for us right now we are dealing only with real numbers, matrices with real entries. So we are only restricted right now with lambda real, okay. So norm of lambda x is equals to mod lambda times norm x. This property is, if you recall, this is also called homogeneity, okay, homogeneity. And norm of x plus y is less than or equal to norm x plus norm y. So if you recall your magnitude, so magnitude is itself a norm, okay, right. So if if you see what is mod function is, mod is from r to r plus, right. And now you know mod x is always greater than 0 if x is non-zero, right. Okay, that's the first property. Second property what we have learned is mod of lambda x is equals to mod lambda times mod x, you know, right. Okay, right. Third property is, you know, mod of a plus b is less than equals to mod of x plus y is less than equals to mod x plus mod y. So you can treat norm as the magnitude of the vector, or you can say length of the vector, okay, right. So here in this is, so R is, you know, R is a set of real numbers, is a field itself is a vector space, okay. It's a R is a vector space, R is a vector field, R is a field, okay. And you know the usual with respect to usual addition and usual multiplication, okay. So that you must have seen during your linear algebra course, okay, right. So as I mentioned, one can think of norm x as the length or magnitude of the vector x, okay, right. So this notion actually generalizes the notion of absolute value for a real or complex number. So that is already you mentioned, right. Okay. So if I recall the set the vector space Rn, okay. So if you choose any two vector from Rn, so you can define the vector addition by adding adding the entries at the corresponding places, okay. So right, so x plus y is obtained by, you can say, you can add the x1 plus y1, x2 plus y2, x on comma xn plus yn, okay. And scalar multiplication is obtained by just multiplying each coordinate, okay. So okay, so right, so alpha x is equals to alpha x1 comma alpha x2 ends on alpha xn, where alpha is any real numbers. We are talking about Rn over R. Rn over R. So Rn is a vector space over set of real numbers. So if you choose Rn over C, it will not be. Okay. So Rn becomes a vector space over R. Right. Okay, so that you can verify that you have seen. So let's define, let's see what are the available norms on Rn. Okay, so one can define various kinds of norms on Rn that you have also seen during your linear algebra course. So norm is very here is one is the Euclidean norm, that is defined by you take the square and then take the square root. And if you recall, okay, if you recall this, what is this? This is the length of the vector, right? If you recall, okay, means you are having x dot product. So you can see, so if I have this is let's say x1 comma x2. So for this case, what is the norm is, if I take this 2 norm, is square root of x1 square plus x2 square. So means length from the origin, right? Vector. Okay. So this is the length. Similarly for on R3. Similarly for R4 and so on. Now the second norm what we have seen is L infinity norm. That's also this is the previous one we'll call also L2 norm. Okay, so if instead of 2 here, if you replace it by P, it is called P norm. Okay, so that we will see later. So maximum norm is defined as, means you take the maximum of magnitude of each entry. Okay, so you take the magnitude of each entry and take the maximum over it. Okay, that will give you the maximum norm. Okay, so right. So for example, for this case, you have let's say this vector 1, 0, minus 1, 2, and 3, this vector in R5. So what is the maximum norm of this infinity norm? Is equals to, you take the magnitude of each entry and take the maximum among this. So magnitude of 1 is 1, 0 is 0, magnitude of minus 1 is 1, magnitude of 2 is 2, magnitude of minus 3 is 3, magnitude of 3 is 3. So maximum is 3. So L infinity norm is 3. Okay. One norm is given by, you take the magnitude of each entry and then take the sum. Okay, so if the same vector norm of 1, 0, minus 1, 2, 3, if I wish to calculate one norm for this is equals to summation of each entry. So mod 1 plus this, so you have 1 plus 0 plus 1 plus 2 plus 3. So right, this is equal to 7. Okay, so but what we have learned, so they are usually they are giving different numbers if you apply the different norms. Okay, but we have seen that they are equivalent to each other. Okay, right. Okay, so what the geometrically mean, if we want to see is them in geometrical shape. If we wish to see unit cells in Euclidean norm or maximum norm or one norm, what it will looks like. So if I say what will be norm of x2 less than equals to 1. So I have choose x belongs to R2. Okay, norm of x2 less than equals to 1. What will be norm of x infinity less than equals to 1. What is the meaning of geometrically for norm x1 less than equals to 1. So what is, if you recall the definition, what is that is a square root of x1 square plus x2 square is less than equals to 1. What will be the unit cell if you draw here is a unit circle. Its interior and its interior. Unit circle. Okay, for this is maximum of either mod x1 or mod x2. So if I have mod x1 is less than equals to 1, okay, So mod of xj maximum over j is must be less than equals to 1. So what will be the corresponding unit cell for this? So either it could be x1 or it could be x2, right? So you have, so if you have mod x, so mod x1 is less than equals to 1. Let's see what is that. Mod x1 is, so you are having 2, so this is x1, this is x2. So mod x1 is less than equals to 1 means minus 1 to plus 1. Similarly, if mod x2 is less than equals to 1, you have mod x minus 1 to 1. So it goes to give you a square unit cell if you look at. Okay, this is less than equals to 1. Okay, this is for this. Now for this, what will be the geometrically? This is mod x1 plus mod x2 is less than equals to 1. And if you look for this case, okay, you will have x1 plus x2 equals to 1, x1 plus x2 equals to minus 1, and you are going to create with x1 minus sign, x1 positive sign. So what are the four possibilities? If you look at x1 plus x2 equals to 1, one line is this, another line is x1 minus x2 equals to 1, other line is you have minus, okay, what is the other line is x2 equals to 0, x1 equals to 1, okay, what will be the other line is, so you are going to choose with all possibilities plus x1 plus minus, so minus x1 plus x2 equals to 1, and other line is minus x1 minus x2 equals to 1. These are the four lines will create the rhombus, this rhombus in itself inside. Okay, right. So this is what the geometrical meaning for or defining this norm into. So this can be understood in this way. Okay, right. So for R3 you can look for that sphere and okay, and cubic cube and so on. Okay, right. So using the norm, so let's take one example using the norm 1. Compare the length of the following three vectors in R4 and then repeat the calculation for norm 2 and norm infinity. So this is one very simple example here. So norm 1, if you calculate for this norm of x, if I say 1 means summation of magnitude. So 4 magnitude, 4 plus 4 plus 4 plus 4, that is 16. If I wish to calculate norm V, that is equal to 0 plus 5 plus 5 plus 5, that is 15. Similarly, norm W1 is equals to 6 plus 0 plus 0 plus 0, that is 6. Okay, now if I wish to calculate norm of x2, norm of x, 2 norm with 2 norm, that is equals to square of each, right? 4 square, 16 plus 16 plus 16 plus 16, each square. So 64, that is equals to 8. Norm of V2 is equals to, so 0 square plus 25 plus 25 plus 25, right? So that is equals to 5 root 3. Now similarly, norm W, 2 norm is square root of 6 square plus 0 plus 0, so it will be 6. Okay, now infinity norm, if you wish to calculate, is norm of x infinity. What is the maximum norm? You take the magnitude of each entry and take the maximum, that is 4, still 4. Norm of V infinity norm is you take the magnitude of each entry and take the maximum, that is 5. Norm of W infinity norm, that is maximum is 6. So these are the values. So if you arrange them in the table, so it's will be more clear. Okay, so infinity norm is maximum norm, 2 norm is you can say the length, okay, and 1 norm is summation of mod of xi's. Okay, right. So if you arrange here, this will be the following. Okay. Okay, so now we are now in a position to define matrix now. Okay, so you can see a matrix, what we understood, a matrix which is arranged in a structure. Okay, and we are only looking for square structure, and so n cross n matrix. Okay, so it belongs to Rn cross n, that also can be looked at Rn square. Means you just continuously push first row, then comma, second row, third row, and so on. So how many number of elements entries are there? N square. So it's also Rn square. Okay, and you can also verify that this matrix space Rn cross n will actually defines a vector space with respect to the matrix addition and scalar multiplication. You know how to perform the addition for the two matrices, and you know how to scalar multiply the matrix. Okay, so verify. Okay, so you are verifying that the matrix, so set of all matrices. Okay, so verify that this m n cross n over R, okay, which is a set of all matrices of order n, okay, with real entries, okay, define is a vector space with respect to usual addition and scalar multiplication, with respect to usual matrix addition. Okay, with respect to usual matrix addition and scalar multiplication. Okay, right. So verify that this Mn cross Nr is set of all matrices of order n with real entries, is a vector space with respect to usual matrix addition and scalar multiplication. Okay, so now we are in position to define a norm on this matrix space. Okay, so where we are clearly mentioning R plus union 0. Okay, so such that for all AB in the matrix space and alpha in the real number, it satisfies the following three. So norm A is greater than or equal to 0. So for any matrix, norm is always non-negative, and norm A is 0 if and only if A is 0. So if A is a null matrix, then only the norm is a 0 number. Okay, otherwise if you have any one of the entries non-zero, okay, then it will be strictly greater than 0. Now second property is, again, is homogeneity. Okay, that's homogeneity. And the third property is triangle inequality. Norm of A plus B is less than or equals to norm A plus norm B. Okay, right. So these are the three definitions, which is the generalized from the norm definition. Okay, right. So if in addition to above, if the matrix satisfies the following property, that norm of A into B is less than or equals to norm A into norm B, then it is called the submultiplicative norm. Okay, then it is called the submultiplicative norm. Okay, so if you, in addition to above three properties, if in addition to above these three, if it also satisfies this, then it is called the submultiplicative norm. So we are going to look which type of, so we are going to identify type of norms, okay, and we see whether it will be submultiplicative or not. Okay, right. So the very first definition is subordinate or induced matrix norm. Why we are calling it induced? You will see soon. So the real valued function, so the definition of norm is defined by, you are taking norm A, if I wish to write it clearly, supremum of norm of A u such that norm of u is non-zero. Okay, norm of u is non-zero. Norm of AU by norm u such that norm of u is non-zero. So you take all non-zero vector, okay, non-zero vector, and see what is this norm here. What is this norm? What are these norm here is? So here this is AU is now is a vector. So u is a vector. Okay, u belongs to Rn. Okay, u belongs to Rn. Okay, so u belongs to Rn. Okay, u belongs to Rn. That we should not forget here. Okay, so u belongs to Rn. So AU is also in Rn, and you know Euclidean norm you have seen. Okay, so if you use one of the norm associated with the vector, then it is called induced matrix norm. Okay, so it's called, this norm is called the subordinate or induced matrix norm associated with the norm B. So this norm could be one norm, two norm, three norm, infinity norm, okay, and so on. Okay, so then we will call them is a, because of this we are calling this is a induced matrix norm. Okay, so here this norm is any norm, okay, on Rn. Now you can verify that this definition, and you have this definition supremum of norm of AU be such that norm of u is 1. Both are same. Okay, so both are same, that you can verify. Okay, means this supremum set and this supreme set both are the same set. Okay, that you can verify at your own. Try it. Okay, or else we will see in doubt session. Okay, right. So from here, what will be your straightforward observation? If you look at here, this definition. So this norm A is defined as the supremum of this. So means whatever the entries is there, it's going to be less than equals to norm A. So from this definition, it is very clear that norm of AU divided by norm of UV is less than equals to norm A for any u. Okay, so what it will give you? It will give you the following. Okay, so it will give you that norm of AXV is always less than equals to norm A times norm XV. Okay, so what we have is, because norm A is supremum of this set. Okay, supremum of this set. So all of the entries here will be less than equals to norm A. You take any. Okay, so norm of AUV divided by norm UV is less than equals to norm A, and norm of U is non-zero number. So you can multiply both sides, so you will obtain the following inequality. Okay, right. Moreover, you can also verify that spectral, if you denote the row of A as the spectral radius of A. How it is defined is maximum of all set of all eigenvalues in magnitude sense. Okay, so the spectral radius is defined as maximum of set of maximum of eigenvalues in magnitude sense, okay, of the matrix A. Okay, so this is here. So how will you verify this? So for this matrix norm, so if I define this norm A clearly, okay, that is supremum of both are the norm AUV, okay, norm of, let me show you the proof for both. U is a non-zero, okay, U belongs to Rn and U is non-zero vector. That's also one of the way. So norm of U is uh, non-zero, I can say. Okay, so from here the first thing, the first inequality is very simple. So this is implies norm of AU divided by norm of UV is less than equals to norm A for all, right? For all U belongs to Rn and norm of U is non-zero. Now you take this norm UV on this side because it's a non-zero number. So this will settle the first inequality. Norm of AUV is less than equals to norm A times norm of UV. So for all U in Rn and norm of U V is non-zero. Okay. So now I can remove this condition norm of U is non-zero. Okay, because if norm of U is 0, both sides are 0 only. Because norm of U is 0 if and only if U is 0. So I can remove this condition now from here. This is also true for norm of U is 0. So this for 0 case, there is nothing to prove. For non-zero vector with non, okay, then we will have this. Now secondly, let lambda, okay, belongs to the set of eigenvalues of A. Means there exists a vector x belongs to Rn, right? X non-zero eigenvector. Also verify that it also have that unit length with 1, that also can be modified, okay, such that Ax equals to lambda x. Okay, so this can be modified, okay, that eigenvector you can make it unit length, right? Okay, so this implies mod of lambda x is equals to, if you see the right side, so mod lambda, so this is vector, so norm time mod of lambda time norm xp, that is equals to mod lambda. And what about the left side? So this implies mod lambda is equals to norm of lambda xv, that is equals to norm of ax v, which you know less than equals to norm a into norm of xv, but norm xv is 1, so that's equals to norm a. So what it gives you, mod lambda is less than equals to norm a, and you have started with an arbitrary eigenvalue of the matrix A. Okay, so every eigenvalue with its magnitude is always less than equals to norm A. So maximum of this also will still less than equals to norm A. So what is the maximum of set of eigenvalues in magnitude sense is called is the spectral radius. So this will give you establish the second inequality. So this implies, so this will implies, okay, mod lambda is less than equals to norm A for every lambda belongs to sigma of A. right? So this implies maximum of lambda belongs to sigma of A of mod lambda is still less than equals to norm A. So this will implies that spectral radius of A is less than equals to norm. Okay, right. This is second inequality what we have seen. Now third thing what we are to now mention is this induced norm, matrix norm, is actually a multiplicative norm. So just now we have seen that norm of AXV is less than equals to norm A into norm XV. Okay, so now what will happen is norm of A times B XV, if you apply, so A and B are both are enclosure matrix, so matrix multiplication is compatible. So if I apply less than equals to, so first you see Bx is a vector and applying A on it, so this is going to be norm A into norm of BXV, right? If I applied this inequality here, so further again I will apply it, so norm of A times norm of B times norm of XV. So what it gives you, this means if precisely norm of AB XV is less than equals to norm A into norm B times norm of XV. And now you have seen that it's you can choose a vector x of length 1. So this is equals to norm of A into norm of B. This is equals to norm of A into norm of B. Okay, if norm of XV is equals to 1. Now look at here. So norm of ABXV is less than equals to norm A into norm B for every x. For every x non-zero and with norm XV1. So its supremum also will be less than equals to this. So this together imply is norm of AB is less than equals to norm A into norm B. So this result is true. So this induced matrix norm is submultiplicative norm. Okay, right. So these are the three things we have seen. Okay, so next we are going to learn the matrix, different type of matrices norm 1, norm 2 and norm infinity, and then Frobenius norm. Okay, so that we are going to learn in the next lecture. Okay, right. Okay, thank you.